Welcome to this lecture on positron emission tomography and computed tomography instrumentation. These are the objectives for this lecture. PET and CT instrumentation is comprised of a PET component and a CT component. Within the PET system, there are also lots of different detectors and types. We'll talk about PET QC and frequency and PET artifacts. And then on the CT part of it, we'll talk about system generations, system configurations, image reconstruction, CT, QC and frequency, and CT artifacts. So first we'll talk about the PET portion of the scanner. These are some PET radionuclides that are commonly used. Of course, the yttrium-86, bromine-76, those are not widely used radiopharmaceuticals. Those are used in research settings. I-124 is predominantly research as well. But the carbon-11, nitrogen-13, F-18, copper-64, gallium-68, and rubidium-82 are widely used. The nitrogen-13, carbon-11, oxygen-13, and rubidium-82. Pay close attention to the half-lives of those. It's very short. F-18 and gallium-68 as well as copper-64 have a more feasible half-life. Part of the problem with half-lives that are really short is it's not feasible for commercial production and transport because the decay is so quickly. So with positron emission tomography, we are imaging annihilation photons that come from positron decay. So these are proton-rich radionuclides. They are neutron deficient within the nucleus. And so within that nucleus, the proton is converted to a positron, a neutron, and a neutrino plus excess energy. The neutron stays within the nucleus of the atom, but the positron, the neutrino, and the energy exit that atom. So there's the chemical equation for that. The positron is emitted from the nucleus, and then it travels a little bit of distance before it runs into an electron and has a secondary annihilation reaction that occurs. With the annihilation reaction, that positron will pair with an electron in an annihilation reaction. The pair, the two 511 keV annihilation photons, will result from that. And basically what happens is the positron is a positively charged electron, and then the electron, just a random electron in nature, it is negatively charged. So the two are highly attracted to each other, but they collide at a high rate of speed, and all of their energy is, or all of their mass is converted to energy in the form of these two 511 keV annihilation photons. Those photons then travel in opposite directions of about 180 degrees from each other. And this will occur anywhere from a few tenths to a millimeter or more from the origin. And so that range that positron travels before it annihilates is dependent on the energy of the positron particle, what kind of matter it's traveling through, and the spatial resolution of PET is greatly dependent on how far that positron is traveling. Time of flight is an important concept in PET imaging. In theory, it is possible to determine the location of the event by determining the time difference of the photon detection. This allows for tomographic reconstruction without mathematical algorithms, and it achieves timing accuracy down to the picoseconds. Sometimes this leads to increased signal to noise ratio, but this is improving greatly with modern scanners. Now, there are a couple degrading factors to spatial resolution in PET. One is the effective positron range. This is the finite range of the positron, and it will travel a distance from that nucleus it was emitted from before it has that annihilation reaction. And the annihilation reaction photons are what we see. We're not able to see that positron decay. So therefore, we're not able to locate the exact location of the annihilation event, or we can get the annihilation event, but not the exact location of where the radiopharmaceutical is actually going and where the positron's occurring. The effective positron range is defined as the average distance from the emitting nucleus to the end of the positron range. The non-collinearity is a term that refers to the annihilation photons really never emitted at exactly 180-degree direction from each other. So early PET scanners were developed in the 1980s. A piece of scintillator was coupled to PM tubes forming detector blocks. Advantage of these systems was allowed the detector elements to be decoded with only 4 PM tubes. This was lower cost and had a fairly decent spatial resolution. With PET-CT scanners, there are about 8,000 to 25,000 crystals. The crystals are 4 millimeter by 4 millimeter, are 4 millimeters by 10 to 30 millimeters. Each detector block will typically be contain 4 crystals and 1 PM tube. And then it either had a bucket or a cassette that grouped the detector blocks. Spatial resolution was approximately 4 millimeters versus 12 millimeters for a gamma camera, although this is greatly dependent on the crystal size and the separation of the crystals. PET scanners are about 50 to 100 times more sensitive than a gamma camera, so they're able to handle a high count rate. Gantry size is about 50 to 70 centimeters. Each bed position is about 15 to 18 centimeters. That bed position is how much anatomy it can cover in at any one time. To compare that to gamma cameras or CT or other modalities, it really refers to the field of view. Each bed position kind of corresponds to what we would consider a field of view. And with oncologic studies, it is typical to have about 5 to 8 bed positions if you're doing a skull to mid-thigh study. The number of bed positions is greatly dependent on the patient's height. So the ideal detectors for scintillation crystals, they should be dense. They should have a high atomic number and a high relative light yield compared to sodium iodine. So they need to be denser than the gamma cameras so that they can trap the high energy photons. And so this is where the high density and high atomic number come into play. That will also help yield a higher light yield, which means it will actually scintillate at the crystal or the detector, and then a short light decay time. It should be able to capture those photons, scintillate them, and then send them to the photocathode or the PM tube so they can end up being counted. PET detectors can either do 2D or 3D mode. 2D uses lead tungsten septa that retracts or goes back in and or extends or retracts. Anyway, so that uses that lead tungsten septa between the rings of the detector. With 2D, it will be less sensitive. And then 3D uses electronic collimation, which means there really isn't any collimator at all, not a physical one, but it will have a very narrow coincidence timing window. And the electronic collimation is a complex reconstruction algorithm, and it allows for a little bit more correction for randoms and scatter to make sure that the photons that are detected are the scintillation photons or the annihilation photons. So this is a PET detector designed for older cameras. You have the crystal here coupled to the PM tubes, and the whole thing makes up a detector block. And then this would be the standard detector block array. With the PET scanner, you have a whole ring of them. So this inside of the donut here is the patient bore. In older cameras, there would have been a germanium rod source built into it for QC. That's right there, and that would kind of retract in and out. And then septa and the detector blocks. So those detector blocks make a ring all the way around the patient. And then the septa are retractable or not, and that's how we determine whether it's going to be 2D or 3D. So these are common types of PET detectors. For time of flight PET, it is only feasible with the modern detector types. BGO has kind of gone by the wayside and doesn't really allow for time of flight. Crystal must have really fast light decay times. The system calculates where exactly the event has occurred on the line of response, and then it improves the image quality significantly. So these are the types. Most of them anymore are these LSO or LYSO detectors, and now you even have digital detectors who use a photodiode instead of a crystal and PM tube system. So the LSOs were doped with cerium scintillation, which increases the scintillation efficiency. And notice that they all had electronic collimation and can do 2D or 3D mode. So the BGO was really the older generation that has kind of gone by the wayside. And most of them now are either these LSO or LYSO crystals, or they have the electronic or their digital scanners. And this is the detector efficiency or the properties of different detector types. The linear attenuation coefficient, of course, the higher the number, the better. So you see sodium iodine thallium is just not good enough for PET. It's not dense enough or thick enough. The GSOs was fairly low as well, but you see the BGO, the LSO, and the LYSO are a lot better. The energy resolution, you'll notice that that is also increased with the newer ones, the LSO and LYSO. The light yield is a lot better. The decay time in nanoseconds is shorter, so that's good. And so that's the chemical composition or the makeup of them is down there at the bottom. This is just another projection of what the PET detector looks like with those rings of detectors. So this one has 4 or 5 rows of detectors that make a ring all the way around the patient. However however many detectors there are in a row kind of determines the bed width or the bed position length. And so the more detectors you have there, the more anatomy you can scan at one time. These are a couple examples of some older PET scanners, a GE standalone PET and then the Siemens PET CT scanner. Modern designs look very similar, although they have gone away from a square more to a round design. The overall design has not changed that much. So when you are scanning for PET CT, you inject that patient with a PET radiopharmaceutical inside their body. That positron decay happens, travels, and the positron will interact with an electron and have that annihilation event. And then the scanner is actually picking up those annihilation photons. As far as the instrumentation is concerned, those are called coincidences because they're looking at the photons that are arriving 180 degrees from each other, opposite detectors at the same time. And so with that, you have 4 types of coincidences, or 4 types of detections that can hit the crystal. And some of them are good and some of them are not. So prompt coincidences is what we really want. That's the total number of events detected by the coincidence circuit. And these are classified as trues, randoms, or scatters. So every single coincidence that occurs every single time that there are 2 photons that hit opposite of each other, that is considered a prompt coincidence. The prompt coincidences can then further be classified as true, random, or scattered. True is what we really, really want. That is a pair of annihilation photons from a single event striking 2 detectors at the same time. And then the random coincidence is a false event. That is when 2 annihilation photons from 2 different annihilation events, 2 different positron decays, just so happen to reach the detectors opposite of each other at the same time, but they originate from 2 completely different atoms or events. This will increase with increased activity, and it will also increase when 3D mode is used because you're not filtering them out as well. And then scattered coincidence originated from the same atom, but one or both scatter and change direction before reaching detectors at the same time, and they're not necessarily can be traced back to the same place. Approximately 50% of photons are scatter. This is really hard for our camera to differentiate, and a lot of times they end up being traced back to the wrong source. If you look over here in the image, this is the scattered ones. It legitimately happened from the same positron decay, and this is a true annihilation event, but this one photon got scattered and ended up all the way over here. So they still hit detectors at the same time. They didn't really hit the right detectors that are opposite of it. So this dotted line makes up the line of response, and this is where the photon would be placed in the patient's body. So those scattered coincidences will end up misplacing counts because of the line of response. It can't really trace back where they came from. The random coincidences we are able to filter out for the most part. These are where, you have one annihilation photon that hits a detector, but not another one. Sometimes you have these randoms that are from 2 different events, and they just so happen to hit detectors opposite of each other at the same time. This is hard for us to filter out, and we don't want it. As you can see, the line of response is placing those photons or annihilation events together, and we don't really want them there. Sometimes we can filter some of that out with the timing window, but sometimes not. And then the true coincidence here on the right is what we want. As you can see that this annihilation event happens, it hits the detectors opposite around the same time, and we're able to count it as an event. This is the PET data acquisition. The attenuation correction can happen in 2 ways. First, there can be a CT attenuation correction map, or you can use a germanium-68 or cesium rod transmission source. Very, very rarely will you see a standalone PET scanner that's not attached to a CT scanner. If it's a standalone PET, then it needs to use the germanium or 68 or the cesium 137 rods for attenuation correction, but CT is better. That's why all PET CTs are all PET scanners that are commercially made are PET CT scanners now, unless you have PET MR. So CT is better. It will decrease the noise and create a really good attenuation map of that patient. It will decrease the overall acquisition time because it takes much longer to do that transmission scan. You get better anatomic information as well. And then the data review, you look at the non-attenuation corrected images, the attenuation correction, and then the CT attenuation images. So you have your CT transmission scan, your attenuation correction, your fused, and then your non-attenuated correction images. And that's typically what you would look at. Now, with PET data acquisition, the coincidence timing window is very important. That's what allows for the time of flight. Typically, it's about 4 to 12 nanoseconds. This is shorter for 3D mode, and modern scanners are getting even quicker. This is estimating the random rate, the acquisition of delayed events or randoms within the timing window of 60 to 100 nanoseconds. And then the single count rates, it measures the single events at each detector. And then the PET sinogram is created. The PET sinogram is corrected for random events, attenuation, scatter events, dead time, and decay that happens in the time that the scan went, because PET radiopharmaceuticals have a really short decay time, so those images end up being corrected for decay. The PET matrix is 128 by 128. QC can be 250 by 256 to increase the resolution. I'm sorry, 256 by 256. PET reconstruction and reconstruction filters the filters are important for PET. The selection of the filter type and the cutoff frequency will depend on the study. Sensitivity affects the quality and the amount of filtering that's required. PET does have a higher efficiency and can be processed with higher cutoff frequencies. Nyquist frequency is an important term. That's the highest frequency that can accurately be represented by the imaging system. In this case, when we're talking about frequencies, we're talking about those sharp cutoffs between areas where there's really hot activity and really cold activity. So it's that quick change. And you'll see that at the border of a tumor or even in the heart, where the heart is really, really hot and the lungs have virtually no radiopharmaceutical in them. So there's that sharp cutoff and contrast between something that's really hot and something that's not. And that's what we were referring to with the frequencies. And because PET has a really high efficiency, it can be processed with higher cutoff frequencies. You're going to have a lot of sharp contrast with PET CT imaging. So the Nyquist frequency term, that is just the highest frequency that can be accurately represented by the imaging system. And so that's an important definition to remember. The background is generated by back projection and mostly eliminated by a ramp filter. The image data can be lower or higher frequency based on the type of study and the radiopharmaceutical distribution. Noise occurs with high frequency. This is unwanted frequencies that are due to statistical fluctuations, and theoretically, this is removed by a user filter. We want to remove as much noise as we can to increase our image quality. So lower count studies will lead to more noise. This requires heavier filters and more filtering to smooth out the images. And then higher count studies will naturally have less noise, so they require lighter filters and less smoothing. There are many quantitative programs that require a specific filter for proper analysis. And examples would be cardiac PET, where we're looking at polar maps, ejection fractions, and wall motion. The optimum filter depends on the study, the patient, and the imaging parameters, the equipment, and the physician preferences. An example would be Butterworth. This is a family of filters for filtered back projection that has the order of power determines the slope of the filtering. A higher a higher one equals a steeper cutoff, and a higher number equals a smoother image. With Butterworth, you also have a critical frequency, and that's the point that the filter frequency equals 0.707, and any lower value equals a heavier filter, which will smooth the images. And the images can be over smoothed or too smoothed. And this may also be different on different imaging systems. Now, in most modern scanners, we have PET-CT, and whenever we have PET-CT, we don't use filtered back projection anymore. We use iterative reconstruction. So if you have a PET-CT scanner, you're using iterative reconstruction. So iterative reconstruction can make better image quality than the filtered back projection for less noise, better resolution, fewer artifacts, and less distortion. Recommendations are for the number of iterations are made by the manufacturer. So it's greatly dependent on which type of scanner you're using. The manufacturer will have recommendations for that. And it uses a 3D post filter to smooth out the images. This can be used for SPECT, PET, or CT, but if you're using PET CT, it's all iterative reconstruction. If new to iterative reconstruction and it's just being introduced, then really you should process it in filter back projection and iterative and compare until you can establish what it should look like. This can remove streak artifacts that occur with filtered back projection. And there are basically 4 steps to iterative reconstruction: a rough estimate of the patient image, creation of projection profiles, comparison of profiles with patient data, updating the computer image to reconcile the differences, and then it will repeat until it gets to the acceptable image. Profiles can diverge with more iterations, creating artifacts or masking others. So it is very important with the iterative reconstruction to follow the recommendations of the manufacturer, and also to compare it to filter back projection if you are new and just introducing it to an existing scanner. There are 2 types of QC for PET, those that are characterization calibrations and those that are corrections. The characterization calibrations are fundamental to the scanner's operation, and it examines the energy, the position, the PM tube gang, and the coincidence timing window. The correction calibrations are there to correct for variations in the scanner and the scaling of images. These would include normalization, blank scan, absolute activity of the well counter, and so forth. So daily QC would be to perform a baseline check and gain the adjustment, perform a blank scan, uniform cylinder or point source scan, and then weekly do uniformity check, well counter calibration check, coincidence timing check, and energy window calibration. And then quarterly, it would need preventative maintenance by a field service engineer, detector efficiency or normalization scan, and cross calibration. In addition to that, there is some PET QC that's done annually. This includes spatial resolution, sensitivity, intrinsic scatter fraction, scatter correction, and count rate performance. And then update of normalization factors and well counter calibration also needs done at least annually, but this may be done more frequently. So daily, it requires a blank scan, and this has correction for calibrations, an air scan or reference scan similar to the daily uniformity flood, quick acquisition of the rod source, and then evaluated visually for abnormal streaks. Weekly, it requires gain settings. This is the amplifier gains of the photomultiplier tubes. and daily is recommended to prevent any sensitivity changes and ensure that a uniform sensitivity response occurs from each direct detector. And then weekly, the coincidence timing calibration will adjust for a timing difference within the event detection circuitry. So you're essentially there testing the coincidence timing window that's used for time of flight and things like that. So the normalization calibration is essentially like a uniformity or uniformity correction blood for SPECT imaging. It is very similar to the high count uniformity that's done on gamma cameras. This is a correction. It's performed with a rod source or germanium-68 filled phantom, and high counts are required, and you have to take a minimum of a 6-hour acquisition. And then quarterly, the absolute activity calibration is done. This converts pixel values into absolute activity per voxel. You use a known amount of radioactivity in a known volume of water inside a phantom, which is then imaged, reconstructed, and processed. This allows for calculation of percentage of injected dose per volume or gram of tissue on patient scans. This allows for the measurement of SUVs of tissues and tumors. So this is an important correction calibration. And then also quarterly, energy window calibration, you'll only operate at 511 keV, and this is performed by a service engineer. Now, there are 3 sources of artifacts with PET, those that come from the operator, those that come from the scanner, or those that come from the patient. With the operator, these could be caused from non-optimal parameters and settings selected, poor QC practices. Within the scanner, you could have electronic malfunctions such as a bad detector block, coincidence processing or sorting electronics, misregistration due to misalignment of the PET and CT. And then examples of patient-related artifacts are patient motion, patient size, metallic objects, or poor patient prep prior to the exam. Now moving on to CT. There are CT, basically you're taking different angular views or projections and adding them together. So PET and CT are very similar in that they're both taking images and angles from several different views and then reconstructing them to add them together. The difference is with PET, the radiopharmaceutical and the radiation are coming directly from the patient as high energy photons, and with CT, the radiation is coming from the machine, and the patient is just attenuating it to create that image. So a little bit about CT history. First one was developed by Jeffrey Hounsfield in the 60s. PET-CT was introduced in the year 2000. The low-dose CT scan is used for attenuation correction and anatomic localization, and high-dose CT is used for diagnostic CT. There are several generations of CT scanners. I'm not going to go through all of them, but you can see them there. The first generation was could really only do the head. It was very slow. It took several minutes per slice, and it couldn't really move that much either. So it just translated across the patient. The second generation is a narrow fan beam with multiple detectors and multiple angle acquisition, but this was still very slow. As it progresses to modern scanners, you may see some 4th generation scanners out there. This is a fan beam with static detectors all around the gantry. Only the tube rotates and allows the ring artifact problems. It avoids the ring artifact problems that happened with the 3rd generation scanners. And then the fan beam is what we see in modern scanners where it does look more like a fan. And we also have helical CTs now where it will spiral around the patient, and this allows for better acquisition, especially if you're catching a bolus. Now recall with CT physics, we have characteristic X-rays and Bremsstrahlung. Bremsstrahlung is that braking radiation, and the characteristic, the X-ray, the electron is ejected from an inner shell. The energy is released as X-rays as the outer shell electrons will drop into the vacancy. Characteristic X-rays require 70 kVp setting or higher based upon the energy of the K-shell electrons. And Bremsstrahlung X-rays can be produced at any projectile electron energy. In diagnostic radiography, most of the X-rays are Bremsstrahlung. And X-ray production relies on 5 factors. The source of free electrons, so you need a hot filament with thermionic emission to kind of boil off those electrons. That requires a high voltage supply to it. The acceleration of electrons, you need a high kilovolt peak or kV to set the potential difference so the electrons will pass from the cathode to the anode. This essentially relates to the energy of the X-rays. Focusing on electrons at the cathode, this is done by using a focusing cup made of molybdenum or nickel that is negatively charged, and it will help direct the electrons to the anode by kind of repelling them and directing them in a certain direction. The acceleration of electrons at the anode, this occurs with bombardment of the target by electrons. So those electrons that got boiled off of the cathode or boiled off and directed towards the anode, they will bombard the anode, and they're basically just interacting with it to force either Bremsstrahlung or characteristic X-ray. And then you have a total energy transfer. The kinetic energy of the accelerated electrons is transferred into thermionic energy and electromagnetic energy. The production of X-rays occurs at the X-ray tube. The filament releases electrons which are accelerated towards the tungsten anode. Electrons will undergo ionization and Bremsstrahlung interactions in the anode. Bremsstrahlung and characteristic X-rays are then directed towards the patient. The operator controls the MA and the potential, or the KVP. And this is a basic layout of X-ray tubes. These examples down here at the bottom are Siemens brand CT tubes. So you have the filament circuit here, and this is where the high voltage supply is applied to it so that it will get really, really hot. And then that filament, once it gets really, really hot, it boils off or releases those electrons. This is where the focusing cup is to kind of focus them directly at the anode. This example here, the anode is made of tungsten. Those electrons will interact with it, and the tungsten anode in CT scanners, that anode will, it's not always made of tungsten, but it will rotate, and that helps to dissipate the heat a little bit because this does require a lot of heat and it generates a lot of heat in this process. And then so the X-rays are produced as these electrons interact with the anode, and it creates that X-ray beam. The other things that you have here, the aperture and the rotating portion, are really there to support the anode, as well as the bearings and the stator electromagnets. And this whole part here is called the glass envelope. As you can see, it doesn't really look like an envelope, it's more of a tube, and that is in a vacuum. And the reason that it's in a vacuum is so all of those reactions that are occurred are kind of pure and controlled, and that there's no, outside factors that are influencing it or causing other reactions to occur. So that's an evacuated gas container, sometimes called the gas or the glass envelope. The cathode is negatively charged. The filament is a current is applied to the filament, and that's where the electrons are produced. And then the anode is positively charged. It's a rotating anode that contains the target materials, and this is where the X-rays are produced. The operator selects the kVp or kilovoltage peak. This is the potential difference between the anode and the cathode. This is the kinetic energy of the electrons as they leave the cathode, and this is the maximum X-ray energy. So the kVp controls the energy of the X-rays that are going to pass through the patient. The MA or MAS, also known as milliamperes, this is the current applied to the cathode filament, and this controls the number of electrons that are released by the anode, and then this eventually corresponds to the number of X-rays that are coming from the machine and the number of X-rays that are being that the patient is being exposed to. So X-rays are produced in that X-ray tube. In CT, the X-ray tube rotates and the detectors opposite the tube measure the X-rays as they pass through the patient. The X-rays are produced and not detected. X-rays that are produced and not detected provide a measure of attenuation of the object or the patient. And so this is where we get the contrast in the image. Not CT contrast, but the image contrast, the different shades of gray, black, and white. And the X-rays are produced when the electron cloud are accelerated across the X-ray tube to interact with the anode. Of the energy applied, about 1% is X-rays and 99% is heat. So it's very important that CT scanners have a good cooling system built into them to keep them cool, keep them from overheating. Many X-rays with many energies are produced, and the low energy X-rays are filtered out by passing through the aluminum filters to decrease the patient dose. Then it goes through the pre-collimators. This defines the X-ray beam shape and width and decreases the radiation dose to the patient. Then all the X-rays will pass through the patient and then arrive at the post-collimators. The post-collimators reduce the amount of scattered photons that reach the detector and decrease the noise in the image. When you're using thinner collimation, this does affect the slice thickness. This has less volume averaging, increased spatial resolution, and decreased streak artifact. Disadvantages of that are thinner collimation. Disadvantages of thinner collimation are an increase in noise, increase in scan time, and also increase in the patient dose. So with CT, the detector array is made up of scintillation detectors. This could be silicon, germanium, cadmium, yttrium, or gadolinium. There are also solid state detectors, so most modern CT scanners would be solid state. These don't have PM tubes, and instead they have photodiodes. There's also a semiconductor junction that detects radiation and generates an electronic signal equivalent to the X-rays. Detectors are aligned in rows. Number of rows will equal the number of slices of the scanner. So 8, 16, 40, 64, and 128 are common. And the DOS, or the data acquisition system, that transmits information to the computer from the detectors. This is a CT scanner, the cover of the gantry of a CT scanner that's been removed for maintenance. I'm unable to play that video, but as you can see from the blurring, it is moving a very, very, very high rate of speed. You want to be really careful and not get close to that. That's pretty dangerous when that moves and the scanner's off. But this is a cross-sectional view. You have the X-ray tube up here with the data measurement system and the detectors down here. Control, the collimator is there between the tube and the detectors, and then you also have that high voltage generator that's supplying the current to the X-ray tube. The CT acquisition has slip ring technology that allows the CT gantry to rotate continuously in one direction while the patient and the bed or the patient bed moves through the gantry. Rotation speed is defined as the time required for one gantry rotation, which is commonly 0.3 to 1 second, and table motion, which is 10 to 20 seconds per minute. The scout, the topogram, or the localizer, that's all the same thing. It depends on the company that makes the CT scanner, but that is the initial scan that's used to select the region for the CT scan, and you'll use anatomic markers to start and stop where the CT is. Now the CT imaging parameters, the kilovolt peak and the milliamperes are set by the technologist. A low dose CT will be about 80 to 140 kVp, but it does depend on the body part that's imaged, the size of the patient, and the position of their arms. A higher kVp will lead to higher X-ray energy, increased penetration of the object, decreased noise, decreased beam hardening, but it will lead to an increased patient dose, and it will also decrease the contrast because you won't see as much attenuation difference in the patient. Now with the milliampere or MAS, a low dose CT will depend on the patient's age, size, height, and weight, but the range is about 20 to 120 MASs. Closer to 400 is the range that you would use for diagnostic CT. So the low dose MAs are sufficient enough. When you increase the MAS, you're increasing the number of X-rays. This will decrease noise and increase the contrast of the image, but it will also greatly increase the patient dose. Noise is also sometimes referred to as quantum model, and this is determined by the number of X-rays. So as you increase the number of X-rays, you will naturally decrease the noise. Now, when it comes to CT image reconstruction, there's a couple important terms. The first one is the Hounsfield units. This compares the tissue's linear attenuation coefficient to the linear attenuation coefficient of water. And so it's basing everything on the density compared to water. So the formula for that is the attenuation coefficient of tissue minus the attenuation coefficient of water divided by water times 1,000. The CT number for water is, or the Hounsfield unit is 0. Air is negative 1,000, and then bone is 1,000. The CT display has a range of CT numbers possible greater than 4,000. The human eye can see 30 to 100 shades of gray, so CT can do a lot more than the human eye can. And the CT display is only a limited range that is set by the operator as the window level and window width. So these are basic CT numbers. Air is negative 1,000, fat is negative 50 to negative 100, bone is 1,000. Water is 0, and then everything else is compared to that. You'll see liver is about 40 to 60. In the brain, there's not a lot of internal contrast because the white matter is negative 20 to negative 30, and the gray is negative 37 to 40. Blood is also 40. Muscle is 10 to 40. kidneys are 30, and cerebral spinal fluid is 15. When it comes to CT image reconstruction, you have the CT field of view, that's the reconstruction diameter. For attenuation correction, maybe a full field of view, about 70 centimeters, or a bit smaller if the CT displayed at the same time. And then a smaller field of view is marked by more magnification. Reconstruction kernel or reconstruction algorithm, it's all the same thing, it's just a different name when it's CT, but this is the algorithm. Sometimes it's referred to as a filter. That's how we more commonly know it in nuclear medicine. But this is just the algorithm that's applied that determines the amount of smoothing during reconstruction. Kernels are selected based on the body part of interest and a defining CT number or defining number. The higher the number, the sharper the image. A reconstructed protocol allows for separate reconstruction of the same raw data using different reconstruction kernels. And this is an example of the kernel or the filter and how that can affect the image. This is the exact same scan, same patient, same body part. A is using a lung kernel or a lung filter, and that's meant to accentuate the darker areas of the lungs so that you can see a little bit more detail and contrast within the actual lung tissue, whereas B is using a soft tissue kernel or soft tissue filter, and that's really just meant to be able to see the rest of the body. So the CT QC daily will need a tube warm up, and it's very important to warm up the CT tube. You cannot produce enough when you're warming up the CT tube. Basically, what you're doing is warming up that filament within the X-ray tube. So if the tube is not adequately warmed up, you cannot have enough thermionic emission of electrons. Therefore, the electrons will not be the correct KVP or MAS, and you won't get good quality images, and you'll get artifacts and things like that in it. So you don't want to use it when the tube is not fully warmed up. If you are in an area where maybe the CT scanner has sat for a while and you do a CT warm up and you think you're fine, but then your images aren't good, then you'll want to do another tube warm up just to make sure that it has had adequate time to warm up. So the first thing that you'll do is the tube warm up before you do anything else. And then verification of the tube output and detector response at various KVP and MAS settings. This is sometimes referred to as air calibrations or fast cals. And then evaluation of tomographic uniformity. This is done using that water phantom. This can also be used to do the CT number accuracy and look at the image noise at parameters used clinically. Other tests that are performed less frequency are the image slice thickness, spatial resolution, linearity of CT numbers, and low and high contrast resolution. Some of these are performed by the physicist, and some of them may be performed by the technologist. So tube warm up is the first thing that's performed. The X-ray tube must be warmed up initially and throughout the day if there is a significant time lapse between scans. Using a cold tube can actually damage that X-ray tube, such as melting the anode or rupturing the tube housing. That's an expensive repair, so always make sure that your tube is warmed up. The cylindrical water phantom is used next. This will test the CT numbers, the noise levels, and the resolution patterns. Images are reconstructed and evaluated visually and quantitatively. Remember, this is CT, so there's no radiation that you have to put into that phantom. It's just a water phantom. And then it should be uniform and free of streaks or rings. It is important to inspect it and review that QC. So image A is showing that high contrast phantom. If you look there in the picture, you're seeing the phantom on the top right, you're seeing the phantom in the holder. And then in image B, you see low contrast resolution, and in C, you see the CT daily uniformity. So I will point out that the high contrast resolution you see in A, it has those several different lines there that allow you to see the contrast resolution, or also known as spatial resolution. B is showing you that with low contrast. There's not a lot of contrast in the image. And then, of course, C is the uniform image. As stated earlier, there are 3 basic sources of artifacts with the CT: the operator, the scanner, or the patient. With the operator, this is a result from inappropriate parameter selection, and that includes KVP, MAS, slice width, increment, and kernel. With the scanner, typically that results from electrical or mechanical operation errors, and these would be ring artifacts, streaks, incorrect mechanical motion, image distortion, or partial volume effects. And then with the patient, the artifacts that occur are patient motion, beam hardening, or metallic artifacts, which will cause a streaking artifact as well. So these are the examples of some artifacts. On the left, you see a metal artifact that's caused by dental fillings. You can see why this is also referred to as a streak artifact, as you have these big streaks that come through. With PET-CT, you will see these, and it can actually create an artifact on the fused images. And you can look at the non-attenuation correction and see that it's not there, and that's one way to differentiate. And then with cardiac PET, you can also see it sometimes from the EKG leads if you're getting really metallic leads. The image on the right is an example of a motion artifact. And you see kind of this displacement in the head and kind of smearing or blurring where the patient moved. And that's it for this presentation. Thank you for watching. I hope you enjoyed this video.